The planets of our solar system have long captured human imagination, but orbiting those planets, hidden in their shadows and bound by their gravity, lies a secret gallery of worlds more extreme, more alien, and more astonishing than the planets themselves. Dozens of moons circle the giant worlds of our system, each one a unique experiment conducted by nature under radically different conditions, each one a world in its own right. Today, we venture beyond the planets, into the shadows, to visit the most extraordinary of these hidden worlds. Our journey will begin on Io, the most volcanically active body in the entire solar system, where the ground itself is alive with fire and the sky glows orange with sulfurous clouds. From there, we will descend to the frozen shell of Europa, beneath whose cracked ice an ocean wider than all of Earth's seas combined quietly waits in the dark. We will then cross to Ganymede, the largest moon in the solar system, a world so vast it dwarfs entire planets, yet one whose greatest secret lies buried beneath hundreds of kilometers of ice. Our path will then carry us to the amber-veiled Triton, the only moon in the solar system wrapped in a dense atmosphere, where methane rains fall from orange skies and rivers run into seas of liquid that has never once touched rock. Then we will approach the geyser-covered south pole of Enceladus, a tiny moon that surprised all of science by venting the ingredients of life directly into open space. And at the end of our journey, at the frozen frontier of the solar system, the doomed world of Triton awaits, a captured wanderer orbiting its planet backwards, spiraling slowly and inevitably toward its own magnificent destruction. Let us begin. The first stop on our journey brings us to a world that looks, at first glance, like a surface scorched beyond recognition, a mottled, smeared terrain of yellow, orange, red, and black, stretching in every direction beneath a sky heavy with sulfurous haze. We have arrived at Io, the innermost of Jupiter's 4 great Galilean moons. Even from orbit, it is immediately clear that this is no ordinary world. The surface below us is restless, shifting, erupting, a landscape that has not been still for a single geological moment in 4 billion years. No craters interrupt the terrain here. Every ancient scar has been buried, resurfaced, and erased by the relentless geological fury that defines this world above all others. Io is the 4th largest moon in the solar system, with a radius of 1,821 kilometers, only slightly larger than Earth's own moon, which measures 1,737 kilometers. Its mass stands at 8.93 times 10 to the 22nd kilograms, approximately 1.5% that of Earth. What makes these modest dimensions extraordinary is what lies beneath. Io harbors the densest interior of any moon in the solar system, with a metallic iron core estimated to span nearly 900 kilometers in radius, wrapped in a thick mantle of partially molten rock that in places reaches temperatures exceeding 1,600 degrees Celsius. Unlike every other moon of the outer solar system, which are composed largely of water ice, Io is almost entirely rocky and metallic, stripped clean of its volatile materials during the violent gravitational chaos of Jupiter's early formation. No feature on Io better captures its volcanic nature than the Great Depression known as Loki Patera. Named after the Norse god of mischief, this lava lake measures approximately 202 kilometers across, wide enough to swallow the state of Massachusetts, and its floor is a slowly overturning crust of solidified lava, disrupted at regular intervals by eruptions that send waves of molten rock across the lake floor in a clockwise direction. Scientists have observed that Loki Patera brightens predictably every 540 days or so, suggesting a cyclical resurfacing event of almost mechanical regularity, a slow, clockwork catastrophe repeating itself since before the first humans walked the Earth. To the east of this great furnace rises the enormous Pele volcano, which has produced a sulfur plume stretching over 1,200 kilometers above the surface, one of the tallest volcanic eruption columns ever observed anywhere in the solar system. The reddish ring Pele has deposited on the surrounding terrain, designated on maps as Pele's Ring, spans nearly 1,400 kilometers in diameter and is composed of short-chain sulfur compounds that rain down from the eruption column and paint the surface in shades of deep crimson. In stark contrast to these fiery lowlands, other portions of Io's surface rise into towering mountain ranges that have nothing to do with volcanism whatsoever. Buo Sale Montes, the tallest peak on Io, reaches 18,500 meters into the thin sky, more than twice the height of Mount Everest above sea level. And it was built not by the eruption of magma, but by compressional forces within the crust, where the constant deposition of new volcanic material buries and compresses the older rock below until the pressure can only be relieved by pushing upward. Io was first observed by Galileo Galilei on the 7th of January 1610 through his newly constructed telescope. He noted it as a point of light near Jupiter, assuming initially it was a background star. Only further nights of observation confirmed it was a moon in orbit. For more than 3.5 centuries, Io remained little more than a bright moving point to the astronomers of Earth. Everything changed on the 5th of March 1979 when the Voyager 1 spacecraft swept past Jupiter at close range and sent back images that stunned the scientific community. Active volcanic plumes rising high above Io's surface captured mid-eruption, the first confirmed active volcanism ever observed on any body beyond Earth. The Galileo spacecraft, which arrived at Jupiter in 1995 and spent 8 years studying the system, transformed our understanding further still, mapping hundreds of volcanic centers, confirming active lava lakes, and measuring Io's extraordinary heat output. More recently, the Juno probe has made repeated close passes of Io beginning in 2023, returning the sharpest images of the moon's tortured surface ever obtained. What makes Io unlike any other world in the solar system is the source of its relentless volcanic energy, because it does not come from where you might expect. Io sits at the gravitational crossroads between Jupiter and its neighbors, Europa and Ganymede, locked into an orbital resonance that means it completes exactly 4 orbits of Jupiter for every 2 made by Europa and every 1 made by Ganymede. This arrangement prevents Io's orbit from ever becoming perfectly circular, forcing it into a slightly elongated path and causing it to flex and deform with every revolution as Jupiter's gravitational pull shifts in intensity. The friction generated by this continuous internal flexing, a process called tidal heating, generates enough energy to melt the moon from within and fuel over 400 active volcanoes simultaneously. Io is not heated by the sun, which at Jupiter's distance provides only 4% of the warmth it delivers to Earth. It is heated by gravity itself. There is no other world in the solar system where tidal forces are so extreme that they have created an entirely molten interior and a surface so rapidly and continuously resurfaced that ancient impact craters have been completely erased, as though the entire geological record of Io's first billion years has been overwritten again and again by the fires below. Leaving the scorched, smoldering plains of Io behind us, we travel outward along Jupiter's orbital path, away from the fires and toward a very different kind of extreme. Our next destination lies just 670,000 kilometers further from Jupiter, a world that appears still and silent and perfectly white, and yet may hold within it the greatest unanswered question in the history of science. We descend now toward a surface that shines with the reflected light of a distant sun, pale and brilliant against the darkness of space. This is Europa, the second of Jupiter's great Galilean moons, and from a distance it appears almost featureless, a smooth white sphere traced with faint reddish-brown lines that cross its face like cracks in a porcelain globe. But those lines and everything they imply about what moves beneath them are precisely why Europa has become one of the most intensely studied and most passionately debated objects in the entire solar system. For beneath that quiet, cracked surface, hidden from the universe under kilometers of ice and utter darkness, something extraordinary is waiting. Europa is slightly smaller than Earth's moon, with a radius of 1,560 kilometers, approximately 44% that of Earth. Its mass is 4.8 times 10 to the 22 kilograms, roughly 0.8% of Earth's. The surface temperature drops as low as 160 degrees below 0 Celsius at the equator and falls still further at the poles. The shell of ice covering the moon is estimated to be between 10 and 30 kilometers thick, roughly the distance between London and Oxford, pressed down in silence over an ocean. And beneath that shell, according to the dominant scientific consensus developed over the past 3 decades, lies a global liquid ocean with an estimated depth of 60 to 150 kilometers, containing an estimated 2 to 3 times more liquid water than all of Earth's oceans, lakes, and rivers combined. Europa's surface is the smoothest of any solid body in the solar system. There are almost no mountains and almost no impact craters. The terrain has been continuously refreshed by a process that churns and recycles the ice from below, erasing the record of ancient collisions as efficiently as Io's volcanism erases its own. The most prominent features are the linea, long, dark reddish streaks and ridges that can stretch for thousands of kilometers across the surface. The most studied of these is a genor linea, a ridge and trough system running nearly 1,500 kilometers along the moon's southern hemisphere, its dark-stained margins believed to contain salts, possibly sodium chloride or magnesium sulfate, that welled up from the ocean below and froze at the surface. Elsewhere, the landscape breaks into what geologists call chaos terrain, regions where the ice crust has fractured into irregular blocks, shifted and rotated in different directions, and refrozen in new positions, like a jigsaw puzzle that has been shaken apart and then frozen mid-reassembly. Connemara Chaos, one of the most extensively studied of these regions, covers an area comparable in size to the American state of New Jersey and shows plate-like ice blocks that have clearly moved relative to one another, suggesting episodes of near-total liquefaction of the ice layer in certain areas. The reddish-brown material that colors the linea and the chaos regions carries a chemical signature, detected by spacecraft instruments, consistent with salts that have migrated upward through the ice from the ocean beneath. Like Io, Europa was first identified by Galileo Galilei in January of 1610, recorded as one of the 4 bright points moving around Jupiter. Its extraordinarily smooth, bright surface puzzled early observers, but the tools to understand it did not yet exist. The Pioneer 10 and 11 spacecraft in the early 1970s provided the first resolved images, confirming its brightness, but little else. It was Voyager 2 in 1979 that revealed the complex network of dark lines crossing Europa's surface and first suggested the possibility of a subsurface ocean. The decisive evidence arrived with the Galileo spacecraft, which between 1995 and 2003 measured distortions in Europa's magnetic field that could only be explained by the presence of a conducting liquid layer beneath the ice, almost certainly a saltwater ocean. 2 major missions are now in transit toward the Jupiter system to investigate Europa in unprecedented detail: the European Space Agency's JUICE mission, launched in 2023, and NASA's Europa Clipper, which departed Earth in October of 2024. The significance of Europa cannot be stated quietly. Beneath those kilometers of ice, in complete darkness and under enormous pressure, liquid water has existed continuously for perhaps 4 billion years. And where liquid water has been present for that length of time, where a rocky seafloor provides chemical energy, and where hydrothermal vents may be actively cycling minerals and heat into that water, conditions that current evidence strongly suggest apply at Europa's ocean floor, life as we understand it becomes not merely possible, but arguably plausible. Europa is not considered the solar system's best candidate for extraterrestrial biology because scientists are being optimistic. It is considered a candidate because it satisfies every single known requirement: stable liquid water, chemical energy, an interface between rock and water, organic compounds, and deep geological time. It is the only place in the solar system beyond Earth where all of these conditions appear to coexist right now. And it has been sitting in our own cosmic backyard, orbiting a planet we have watched since ancient times, waiting for us to notice. We lift away from Europa's silent, cracked ice and continue outward, deeper into Jupiter's gravitational family, where an even larger world is waiting, one whose sheer scale challenges the definition of what a moon is allowed to be, and whose hidden interior contains a secret that no one expected to find this far from the sun.